Welcome to On Chemistry. We are seeing organic chemistry concept. In this video, we are going to see Baeyer Villiger Oxidation Rearrangement reaction. The reaction is important organic rearrangement reaction. The concept is fully explained using 52 examples, those examples from various examinations. It will help you to understand the concept much better. What is inside this video? First, we will see what is Baeyer Villiger oxidation and mechanism behind the rearrangement, then basics, which include migrating ability, steric effect, cyclic system. Then very important thing is we are going to solve 52 examples from various examination. This is very important. It will give you different perspective and deep understanding. First, we will see what is Baeyer Villiger oxidation. It is a conversion of ketone into ester in presence of peracid. Here, starting material ketone is shown. Peracid. Peracid means extra O with an acid. It donates the oxygen. Then it converts ketone into ester. The facts about the reaction is it is an oxidation reaction. It involves rearrangement. The R group or alkyl group migrates. It's a functional group conversion also because you are converting ketone into ester. The catalyst can be anything: peracid, substituted peracid, even aromatic acid or simple peroxide or substituted benzene acid. Basically, the compounds donate oxygen. Mechanism behind the reaction is simple. The starting material is ketone. You are attacking with peracid. So nucleophilic addition to the carbonyl happen. New CO bond. Then O minus is there. The carbon with many heteroatoms. So what is the problem here? How can be solved here mean anion can be a ketone. Methyl migrates to the oxygen and RCOO minus eliminates. We end up with final ester. If you read down nicely, you can clearly see ketone converted into ester. Here three things happen concerted way: migration of methyl group, RCOO minus elimination, and carbonyl formation. The mechanism may or may not be concerted. Both mechanism will give same answer. The mechanism may be detailed, but the writing product is very easy. What you should do: starting material is ketone. First you should find the migrating group. Which group migrates, you should identify it. Near to the migrating group, just insert the oxygen. So ketone converted into ester by the insertion of oxygen. So you just find the migrating group, insert the oxygen. That is the easy trick to find the product. Then we will see migrating ability. Suppose you have the ketone with two different attachments. One is methyl, one is isopropyl. You are using the condition for Baeyer Villiger oxidation. But the question is which group migrate? Methyl migrate or isopropyl migrate? That is technically called migrating ability. The group migrate is called migrating group. Mostly cation stabilizing species migrate or electron rich group migrate. So isopropyl is much more electron richer because of attached methyl group. So major product will be migrating group with cation stabilizing tendency. We will see that. So the migrating ability can be summarized simply: electron rich group migrate. In alkyl system we know tertiary cation is more stable. So same way here tertiary migrate first, then secondary, then primary. In phenyl system, ether, then methyl, then simple benzene, then nitrobenzene. Basically electron density in the benzene ring. Overall if you look at it, hydrogen migrates first, then tertiary, then cyclohexyl, then secondary, then benzyl, aromatic, primary and methyl. Basically you are going from high electron density to low electron density. Then the important fact is cyclopropyl cation. The cation is aromatic, so extremely stable. Let us see why. Here cyclopropyl is the squeezed strained full system. The bonding orbitals are perpendicular due to the bond angle. So the cation can rotate, stabilize itself, basically like delocalization in the benzene ring. Cation stabilizes. Here I shown 2 electron rotate. If you look at it, 2 electron mean it obey the Huckel rule, which is 4n plus 2, where n is 0 with 2 electron. In organic chemistry, stable cation is the aromatic cation. So aromaticity is established. Cation is very much stronger. So whenever you see cyclopropyl group, migrate first. Then short note on steric effect. It can affect the migrating ability by the fact you will migrate cation stabilizing species, but bulky group cannot move as well as cannot migrate. Here is on the bicyclic system is tertiary butyl. Tertiary butyl in the bridged carbon. So the approach and migration is harder. So minor product is the major product here. Major product is ring expansion with other side. So steric effect can dominate the migration. So whenever you see steric effect, avoid it. Find the major product which is less steric product. Then the interesting fact, what will happen if the migrating group is the chiral carbon? Here is shown chiral carbon which is attached with hydrogen, carbonyl, methyl and ethyl. What will happen once it migrates? Whether retention or inversion of configuration happen. Here mechanism is mostly concerted, so no change in the migrating pattern. So the chiral carbon don't change. Here you start with R, end up with R, no change in configuration. So in Baeyer Villiger oxidation, there is no change in the migrating group. The configuration is preserved. Then the final basic. If you are in the cyclic system, the ring always expands. Strain also sometimes help for the expansion. Suppose you have ketone in the cyclic system, you end up with lactone. The ring expansion with one oxygen atom because you are inserting the oxygen. That's why ring expansion. Here I shown 5-member ketone becomes 6-member lactone by the expansion with oxygen. Same will happen with 6-member to 7-member. So whenever you have cyclic system, ring expansion happen. Then we are going to see very important thing, 52 fully solved examples with mechanism. Why we are solving so many questions? Because problems are best way to learn. You will have different perspective, complete understanding of concept. So I given from various examination. It will help you to understand concept much deeper. Let us see the first example. Here you have ketone, both sides attached with phenyl. Here you are using the peracid of acetic acid. You should find what will be the final product. By looking at the carbonyl and peracid, you might realize Baeyer Villiger oxidation rearrangement reaction. Here I shown the non-concerted mechanism. You can show in the both way. For initial understanding, I shown non-concerted mechanism. Here you have carbonyl, you are using the acid. So addition reaction happen. Nucleophile add to the carbonyl. You end up with addition. Then you have carbon with many heteroatom. So it has to be stabilized. So leaving group leaves, migration happen. So cation forms. Cation has to be quenched. Cation quenched as carbonyl. You end up with ester. If you redraw nicely, you have phenyl ester. Then the next example. Here you have cyclohexanone. You are using the peracid. You should find what will be the final product. The starting material is ketone. You are using the peracid. So it's a Baeyer Villiger oxidation. First step will be attack of nucleophile to carbonyl. Nucleophile is peracid. It attacks. You have new CO bond with O minus. The carbon with many heteroatom. It has to be stabilized. So O minus forms the carbonyl. So carbon migrates, which is first step. Then CH3COO minus eliminates. And third step, CO formation is shown as the concerted mechanism. So if you find finally, you have lactone there. So lactone expand the ring. If you redraw nicely, you end up with 7 member. So start from 6 member ring, end up with 7 member ring. The concept you have to learn here is in Baeyer Villiger oxidation, ring expansion happen in the cyclic system. Then the next example, here you have ketone, one side methyl group, another side carbon with one methyl and phenyl. Carbon is above the plane, you are using the peracid. You should find what will be the final product. Here the problem in the blind side. Here carbonyl is there, peracid you are using. So definitely Baeyer Villiger oxidation. But the starting metal is tricky because geometry of hydrogen is not specified. Since hydrogen is missing, you redraw with hydrogen and geometry. Methyl above the plane, hydrogen below the plane. So you are using the peracid. First step will be nucleophilic addition on carbonyl. New CC bond form with O minus. The carbon is attached with two different attachments, which is asymmetric carbonyl. Which group migrates? Here, chiral carbon is the stabilizing carbon because it is with phenyl as well as many carbon atoms. So it will migrate. Since the carbon is unstable, it promotes the migration. So tertiary carbon migrates, CH3COO minus eliminates, then CO forms. All are concerted. All three steps happen simultaneously. You end up with ketone. If you read down nicely, you can clearly see there is no change in the configuration because you start from R configuration, end up with R configuration. The concept you have to learn here is if the migrating group is the chiral carbon, there will be no change in the configuration. So Baeyer Villiger oxidation occur with retention of configuration. Then the next example. Here you have cyclohexanone with two methyl group in alpha beta position. Two methyl groups are seen above the plane. You are using the peracid. You have to find what will be the final product. Here you have ketone and you are using the peracid. Definitely Baeyer Villiger oxidation reaction. The starting metal ketone which is asymmetric, one side with secondary carbon, another side with tertiary carbon with different stereochemistry. So the first step will be attack of RCCO minus in carbonyl which is nucleophilic addition reaction. New CC bond form with OH. Here the carbon attached with many heteroatom mean the cation stabilizing carbon migrates. So it migrates. You have cation near the alcohol. Here it is non-concerted mechanism. So the migration happened. Cation considers carbonyl there. So ring expanded. So you redraw nicely. You have beautiful 7 member ring with same stereochemistry. Here stereochemistry given for distraction because reaction center is away from stereochemistry. The concept you have to learn here is in cyclic system, ring expansion happen in Baeyer Villiger oxidation. Then the next example. Here you have ketone, one side methyl group, one side phenyl. You are using the peracid. You should find what will be the final product. Starting material is ketone. You are using the peracid mean Baeyer Villiger rearrangement reaction. First step will be RCOO minus attacks. You have new CO bond. Here carbon with many heteroatom and starting material also asymmetry ketone. So one cation stabilizing group migrate should form stable carbon. Here phenyl can stabilize the cation better. So phenyl migrates to oxygen. ROO minus eliminates. You have cation near the alcohol. Cation considers carbonyl with hydrogen elimination. End up with ketone there. If you redraw nicely, you have oxygen inserted between phenyl and carbonyl. The concept you have to learn here is phenyl has higher migrating ability than methyl. Then the next reaction. Here you have bicyclo compound with ketone. Ketone at the bridged carbon. You are in the peracid. You should find what will be the final product. Here you have ketone and peracid. Definitely Baeyer Villiger oxidation. Here reaction is special because carbonyl in the bridged carbon. So what will happen if it is in the bridged carbon? Nothing. We will go with the mechanism. We will find the final product. First step will be attack of acid to the carbonyl. So new CO bond formed with OH minus. Then carbon with many heteroatom. It has to stabilize itself as well as ring strain is there. 5 member becomes 6 member. So ring open. You have new CO bond. Then cation near the alcohol. It is quenched as carbonyl. You end up with lactone. If you read on nicely, you can see bridge is expanded. 5 member ring will become 6 member ring. The reaction is assisted by the strain. The concept you outlined here is Baeyer Villiger oxidation can happen in the bicyclic system. Then the next example. Here you have fused system, benzene and cyclohexane. Cyclohexane has diketone as well as alkene. You are in the peracid. You should find what will be the final product. Here the starting middle is very much interesting because you have two ketone. Which ketone will be reacting? Here I labeled as A and B. Here A positive charge delocalized to the benzene ring, so not available for the attack. So B carbonyl reacted, not the A carbonyl. Here chemoselective. If you compare A carbonyl and P carbonyl, A carbonyl positive charge delocalized in the benzene, so it is not available for the attack. So only P carbonyl reacts, not the A carbonyl. So the attack happened. You have new CO bond. Then it is unstable. So methylene group migrates. Here carbonyl carbon migrate. You have cation near the alcohol. The cation has to be quenched. So alcohol becomes ketone. If you read it nicely, we end up with 7 member ring. You are starting from 6 member diketone. You end up with 7 member anhydride. The concept you outlined here is the carbonyl with high positive charge will be attacked by the nucleophile. Then the next example. Here you have ketone. One side methyl group, another side chiral carbon with methyl, ethyl, hydrogen. You are using the peracid. You should find what will be the final product. Here carbonyl is there. You are using the peracid. So obviously Baeyer Villiger oxidation. First step will be attack of nucleophile. Nucleophilic addition to the carbonyl. New CO bond. Here the carbonyl is asymmetrical carbonyl. Which carbon migrates? The cation stabilizing carbon migrates. Chiral carbon is secondary. It is migrating. You have new CO bond as well as carbonyl as well as CH3COO minus elimination. So you end up with ester there. Here starting material with R configuration. Product also R configuration. There is no change in the chiral carbon. It is a retention of configuration. The concept you outlined here is in Baeyer Villiger oxidation. If the migrating group is chiral carbon, means there will be no change in the configuration. This all possible because of concerted mechanism. Then the next example. Here you have aniline. You have ketone in the system. It is a 11 carbon system with ketone. You are using the peracid. You should find what will be the final product. Here compound is big, but our functional group is carbonyl. So same reaction, same mechanism. First step will be attack of acid. You have new CO bond. There the carbon with many heteroatom. It is unstable. So the carbon migrate and cation form. Cation quenched as the carbonyl because OH and cations are nearby. The quenching leads to the carbonyl. You start with ketone, end up with ester. But interesting fact here is ring expansion. 11 member ring will become 12 member by the insertion of oxygen. Here you need not to worry about migrating ability because both carbons are same. And the fact you should learn here is symmetrical carbon migrating ability does not matter. Then the next example, here you have cyclohexanone, fourth position you have methyl group, peracid you are using, you should find what will be the final product. Similar examples we seen, here ketone is there, you are using the peracid, first step will be nucleophilic addition on carbonyl, the addition leads to the new CO bond. The carbon with many heteroatom, it is unstable. So ring methylene group migrate. The migration leads to the cation near the alcohol. Hydrogen eliminate, it considers ketone. The interesting fact here is ring is expanded by the insertion of oxygen. So you start from 6-member ring, end up with 7-member ring. The molecule is symmetrical, so migration of any carbon leads to the same product. The concept you have to learn here is in Baeyer Villiger oxidation, ring system always will expand to next size. Then the next example, here you have bicyclic ketone with bridged carbon, 2 bridged methyl group, 1 ketone. You are using the peracid. You should find what will be the final product. Here ketone and peracid, you might realize it's a Baeyer Villiger oxidation rearrangement reaction. The first step will be attack of acid to the carbonyl. It's a nucleophilic addition reaction. So new CO bond forms. It makes carbon atom unstable. So the carbon in the ring has to migrate. Which ring migrate? The cation stabilizing species migrate. Here tertiary and secondary carbon is there. Tertiary can stabilize better. So it migrates. You have cation near the alcohol. It considers carbonyl by hydrogen elimination. Since the hydrogen insertion happened, ring size expanded. You have ring expanded bicyclic compound. The concept you have to learn here is Baeyer Villiger oxidation can happen in the bicyclic system. Then the next example, here you have fused system with cyclohexane and cyclopentane. 4 rings are there with 2 methyl group and 1 ketone. You are using the peracid. You should find what will be the final product. Here structure may be big, but all the fundamentals same. So don't get intimidated by the big structure. You focus on functional group and mechanism. Here acid is there, ketone is there. So Baeyer Villiger oxidation. First step will be attack of acid to the carbonyl. So you have new CO bond. The addition leads to the carbon unstable. So one carbon should migrate for the stability. Here two sets of carbon is there, secondary and tertiary. As we learned already, tertiary can stabilize the cation better. It migrates. You have cation near the alcohol. So migration happened. Cation near the alcohol considers carbonyl by the hydrogen elimination. So ring expansion happened. 6-member becomes 7-member with ester. End up with final product. The concept you have to learn here is in Baeyer Villiger oxidation, cation stabilizing group migrates. Then the next example, here you have cyclohexane and acyl group attached there. Both are syn to each other. Methyl and acyl group attached in 1,2 position. Both are syn to each other, stereochemically specified. You are using the peracid. You should find what will be the final product. As we discussed already, our focus is on carbonyl. So carbonyl is there, acid is there. So Baeyer Villiger rearrangement reaction. First step will be as usual. Nucleophile attacks the carbonyl. It's a nucleophilic addition reaction. It makes the carbon atom unstable. So one carbon should migrate it to stabilize it. Which carbon migrates? Because you have tertiary and primary. As per the migrating ability, tertiary will migrate because it can stabilize the cation better. So migration happen. You have cation near the alcohol. Then alcohol considers carbonyl. End up with ester. If you redraw nicely, you have syn compound with methyl and ester. The concept you have to learn here is you just focus on functional group and reaction mechanism to find the perfect product. Here stereochemistry given as distraction. It don't contribute anything to the mechanism. Then the next example. Here you have bicyclic system. Two methyl group unbridged carbon, one methyl unconnected carbon, and you have ketone. You are using the peracid. You should find what will be the final product. Here ketone is there, peracid is there. Definitely Baeyer Villiger oxidation rearrangement reaction. Ketone and acid, nucleophilic addition on carbonyl. Since the oxygen addition makes the carbon unstable, carbon migrates. You have cation near the alcohol, but which group migrate is the interesting question. Instead of tertiary, secondary migrated. Why? Because tertiary is very crowded. Even though it has higher migrating ability, secondary carbon migrate. If you look at the normal standard reaction, tertiary carbon can stabilize the cation better than secondary. Due to the steric effect domination, migrating ability is reversed. Here secondary migrated, not the tertiary. The concept you outline here is in Baeyer Villiger oxidation, steric effect has higher priority than the migrating ability. Then the next example, here you have ketone, one side toluene, another side nitrobenzene. You are using the peracid. You should find what will be the final product. The reaction is tricky in terms of migrating ability, but we will go by fundamental facts and mechanism. The starting material is ketone, acid is there, so Baeyer Villiger oxidation. So nucleophilic addition and carbonyl happen, new CO bond forms. Then the addition leads to the carbon with many heteroatoms. It makes the carbon unstable. So one carbon migrates to stabilize it. Which carbon migrates is the real question here. Whether methyl benzene migrates or nitrobenzene migrates. Here methyl is the electron donating group. Nitro is the electron withdrawing group. Nitro group destabilizes the cation. Methyl group stabilizes the cation. So toluene migrates to the oxygen. CH3COO minus eliminates. O minus forms CO. All are shown as the concerted mechanism. 1, 2, 3 steps. You end up with ester there. So oxygen insertion happen on the methyl side. The concept you have to learn here is in substituted benzene system, electron donating species migrate. Then the next example, the starting material is ketone. One side you have tertiary butyl, another side you have phenyl. You are using the peracid. You should find what will be the final product. Here you have ketone and peracid you are using. So Baeyer Villiger oxidation. So first step will be addition of peracid to the carbonyl. New CO bond forms. The addition leads to the carbon unstable. So carbon should migrate to stabilize the carbon. So carbon migrates to stabilize the carbon. Which carbon migrates is the interesting question. Whether phenyl migrates or tertiary butyl migrates. Tertiary butyl has higher priority than phenyl, so it migrates. ROO eliminates. Cation formed near the alcohol. The cation considers carbonyl by the hydrogen elimination. So you start with ketone, end up with ester. Ester on the tertiary butyl side. The concept you outline here is tertiary butyl has higher migrating ability than phenyl group. Then the next example. Here you have bicyclic system, two methyl group on the bridge. Side chain above the plane you have ketone. One side bicyclic system, another side phenyl peracid you are using. You should find what will be the final product. Here system may be bicyclic, but the reaction center is outside the bicyclic system. We will go by fundamentals as well as basic mechanism. So we stick with fundamentals and basic. Peracid is there, carbonyl is there. Peracid attacks the carbonyl through the nucleophilic addition reaction. So new CO bond which makes the carbon unstable because it is attached with many heteroatoms. So to stabilize the carbon, any carbon should migrate. Here the competition between phenyl and bicyclic system. As we seen already, tertiary butyl has higher migrating ability than phenyl group. Tertiary butyl group, which is the bicyclic carbon, migrate. You have COO elimination and cation near the alcohol. So cation has to be quenched. It quenched as carbonyl. So you start from ketone, end up with ester. You have the final product. Here the stereochemistry given as the distraction because the carbon is not chiral. Since both carbons are same, it is achiral. The concept you have to learn here is tertiary butyl has higher migrating ability than phenyl group. Then the next example. Here you have fused system. Two cyclopentane fused together. One methyl group, one ester group. Alkene is there, ketone is there. Many functional groups. You are using the peracid. You should find what will be the final product. Here you have two carbonyl in the system. One is ketone, one is ester. So chemoselectivity is required according to the carbonyl reactivity. If you look at the carbonyl reactivity, ketone is more reactive than ester because ester has electron donating oxygen which quench the positive charge. So ketone is reactive. So it is chemoselective reaction. Only ketone reacts. So peracid attacks the ketone, not the ester. You have new CO bond. The addition leads to the many heteroatom on the oxygen. So carbon has to migrate. Which carbon migrate? You have tertiary and secondary. Tertiary also a chiral carbon. Cation stabilizing species migrates. Tertiary can stabilize better. Tertiary migrates. Since the carbon is the chiral carbon, mechanism also concerted. You end up with retention of configuration. The migration leads to the cation near the alcohol. It quenched as carbonyl. So final product, if you look at it, you have lactone with methyl group with retention of configuration. So methyl don't change its configuration. Starting material and product both are same chiral carbon. Baeyer Villiger oxidation happened. The concept you have to learn here is ketone is more reactive than ester. Baeyer Villiger oxidation prefer the ketone. Then the next example, you have cyclopentanone peracid you are using. You should find what will be the final product. Here ketone is there, peracid is there, ring system. So obvious choice of Baeyer Villiger oxidation. We will go step by step. First step will be nucleophilic addition on the carbonyl. The addition leads to the new CO bond which makes the carbon unstable. So one carbon should migrate. The system is symmetrical. Both carbons are same. We can migrate anything. Result will be same. So carbon migrates. You have cation near the alcohol. Cation quenched as carbonyl by the hydrogen elimination. You end up with carbonyl. So if you redraw nicely, you end up with ring expansion. The concept you have to learn here is in Baeyer Villiger oxidation, symmetrical carbon migrating ability does not matter. Then the next example, here you have ketone which is in the bridged carbon. The system is bicyclic system. One side with 3 carbon, another side also 3 carbon. with one bridged carbon. The bridge contains carbonyl. You are using the peracid. You should find what will be the final product. The starting material contains ketone in the bicyclic system. You are using the peracid. So Baeyer Villiger oxidation. First step will be nucleophilic addition on carbonyl. H and RCCO minus attach. It form new CO bond which makes the carbon unstable. So one group migrates. Since the system is symmetrical, both carbon migration leads to the same result. One carbon migrates. You have RCOO elimination as well as cation near the alcohol. The cation quenched as carbonate. You end up with bridged ester. The bridge also expands because you have new insertion of oxygen. So ring expansion happen. The concept you outlined here is in bicyclic system also Baeyer Villiger oxidation can happen. Then the next example. Here you have cyclopentanone. Alpha position you have methyl group. You are using the peracid. You should find what will be the final product. Here ketone is there. You are using the peracid. So Baeyer Villiger oxidation reaction. Here starting material is the carbonyl. You are using the peracid. So Baeyer Villiger oxidation. First step will be nucleophilic addition on the carbonyl. RCOO minus adds new CO bond forms which makes the carbon unstable. So one carbon should migrate. Which carbon migrates? The cation stabilizing tertiary carbon migrates. So tertiary carbon migrates. You have new OC bond. The migration leads to the cation near the alcohol which form ketone by hydrogen elimination. Since the oxygen insertion happened, you have ring expansion. The concept you outlined here is in Baeyer Villiger oxidation, cyclic system always expand to the next phase. Then the next question. You have cyclohexanone. Second position you have phenyl which is below the plane, stereochemically specified. You are using the peracid. You should find what will be the final product. Here you are having the carbonyl and you are using the peracid. So nucleophilic addition to the carbonyl happened. So RCCO minus adds to the carbonyl. OH also form. The addition forms new CO bond which makes the carbon unstable. So carbon should migrate. Which carbon migrates? Tertiary carbon which is stereochemically specified with phenyl migrate because it can stabilize the cation better. So it migrates. It forms cation near the alcohol. Cation quenched as carbonyl by the hydrogen elimination. The migration makes the ring bigger. 6-member ring will become 7-member ring. Here no change in chiral carbon happened because retention of configuration is favorable in Baeyer Villiger oxidation. Here two facts you should learn. One is chiral carbon makes it retention of configuration. Another is benzyl carbon has higher migrating ability than the secondary carbon. Then the next example. Here you have bicyclic system with one bridged carbon, two methyl group on one side, one methyl group on the connected carbon. You have ketone in the middle. You are using the peracid. You should find what will be the final product. Here ketone is there, peracid is there. First step will be nucleophilic addition, that is Baeyer Villiger oxidation. The addition leads to the new CO bond. So one carbon migrates to stabilize it. So which carbon migrates is the real question. Both carbons are asymmetrical, but one carbon is very much steric. Steric prevent the migration. Ring rigidity also prevent the migration. So less steric carbon migrates. Migration happen on the methyl bridge. Migration happened. RCOO minus eliminate. You have cation near the alcohol. The cation has to be quenched. It quenched by H plus elimination with carbonyl. The concept you have to learn here is steric effect has higher priority than migrating ability. Then the next example, you have ketone which is cyclohexanone. Second position you have acid with methylene group. You are in the peracid. You should find what will be the final product. The Baeyer Villiger oxidation is given, but in the hidden form. Here you are having acid, you are in the peroxide. Peroxide convert acid into peracid. So you have peracid, which is reagent. Carbonyl also in the same system. So intramolecular Baeyer Villiger oxidation is possible. Acid attacks the carbonyl. New cyclic system attacks. You have new CO bond. The mechanism is same, only intramolecular. The attack leads to the carbon unstable. One carbon migrates. Here, tertiary carbon can migrate better than secondary carbon. It migrates. You have new CO bond and cation. It also leaves the COO minus, which converts into acid, and cation near the alcohol. The cation quenched as carbonyl end up with ring expansion. So paracid carbonyl in the same system. Baeyer Villiger oxidation happened. The concept you have to learn here is always master the fundamental. Then only you can solve tricky organic conversion reaction. Then the next example. Here cyclohexane is given, which is in the chair form. You have one isopropyl, one methyl group. You are using the peracid. You should find what will be the final product. Here also the tricky question, but stick with fundamentals. Here simply you have ketone and acid, so chances of Baeyer Villiger oxidation. First step will be attack of acid. You have new CO bonds. The new CO bonds makes the carbon weaker because it is attached with many heteroatoms. So one carbon should migrate. Which carbon migrates? Migrating ability decided by the ability to stabilize the cation. So tertiary carbon can stabilize the system better. So it migrates. You have new CO bond or COO minus elimination and cation near the alcohol. The cation has to be quenched. It quenched as carbonyl. The concept you outline here is sometimes structures can be twisted, but stick with fundamentals. Here cyclohexane in chair form is given, but nothing will change according to our mechanism. Stick with fundamentals. Find the final product. Then the next example. Here you have benzene. It is fused with cyclopentanone in 1,2 position. You are in the peracid. You should find what will be the final product. As we discussed already, we stick with fundamentals. Ketone is there, acid is there. So Baeyer Villiger oxidation. First step will be attack of acid to the carbonyl. You have new CO bond. The formation leads to the carbon instability. So one carbon migrates to stabilize the carbonyl carbon. Which group migrates? The cation stabilizing group migrates. So phenyl migrate. You have cation near the alcohol. The cation quenched as carbonyl end up with cyclic ester, that is lactone. If you redraw nicely, you can clearly see the ring expansion. So you start from 5 member, end up with 6 member. So ring strain also relieved. So the reaction completely assisted by the ring strain because 5 member strainful ring becomes strain free 6 member ring. The concept you outline here is if strain in the system can assist the Baeyer Villiger oxidation. Then the next example, here you have benzene attached with 4 member ring which is below the plate. You have the ketone. You are using the peracid. You should find what will be the final product. The starting material is ketone. You are in the peracid. So Baeyer Villiger Oxidation. Here 4-member ring with stereochemistry because sp2, sp3 and ring carbon all create the strand. So ring is kind of twisted. That's why stereochemistry. Peracid attacks the carbonyl, form new CO bond. Addition makes the carbon unstable. So one methyl group migrates, which will migrate. Phenyl group can migrate better than methylene. So phenyl migrate. RCOO minus eliminates. You have cation near the alcohol. If you notice, you have 4-member ring in the system. During the process, ring expand to 5-member. So it goes from strainful system to less strainful system. So the reaction can be assisted by the strain, promote the final product. The concept we outlined here is strainful system relieved during the Baeyer Villiger oxidation. Then the next example, you have benzene, side chain you have ketone with methylene and benzyl carbon with one methyl group above the plane. You are using the peracid. You should find what will be the final product. Here starting material is ketone. You are using the peracid. So Baeyer Villiger oxidation reaction. Nucleophilic addition on the carbonyl. It forms new CO bond and OH, which makes the carbon atom unstable. So one carbon should migrate. Which will migrate? The cation stabilizing carbon migrate. Here tertiary carbon and primary carbon is there. Tertiary migrates. So you have chiral carbon migration. But as we discussed already, with the retention of configuration, chiral carbon stay as the same without change its original configuration. The migration leads to new CO bond as well as cation near the alcohol. Cation considers carbonyl by the hydrogen elimination. You end up with ester. All the things happening in the side chain. Phenyl ring is just there, but only fact is stereochemistry of chiral carbon is preserved. The concept we outlined here is in Baeyer Villiger oxidation, retention of configuration happened. Then the next example. Here you have ketone, one side methyl group, another side you have alkene, that is alpha beta unsaturated ketone with side methyl group. You are using the peracid. You should find what will be the final product. Here the question is all about migrating ability, but we will go by the basics. The starting metal is ketone. You are using the peracid. So Baeyer Villiger oxidation reaction, carbonyl attacked by the acid. You have new CO bond, make the carbon weak. So the migration of carbon occur for the stability. So which carbon migrate? Whether methyl or allyl. Allyl can stabilize the cation better. So allylic migration happen. You have cation near the alcohol. Here sp2 bond breaks, but allyl can stabilize better. That's why transfer happen. So you end up with ester in the side chain with alkene. The concept we outlined here is migrating ability of allyl is higher than the primary. Then the next example. Here you have cyclobutane. First position you have ketone. Third position you have methyl group. You are using the peracid. You should find what will be the final product. By looking at the carbonyl and peracid, you might realize it's a Baeyer Villiger oxidation. First step will be nucleophilic addition on carbonyl. New CO bond forms RCOO add to the carbon, hydrogen add to the oxygen. Simple nucleophilic addition. The addition leads to the carbonyl unstable because carbon attached with many heteroatoms. One carbon should migrate. Since the system is symmetrical, the nearby carbon migrates. You have ring expansion. Here you should know the fact that 4-member ring is highly strainful because of ring strain. The migration leads to the ring expansion because oxygen insertion makes the ring 4-member to 5-member. So strain is relieved. So the reaction can be called as strain-assisted reaction. The ring expansion leads to the cation near the alcohol. It quenched as carbonyl. If you read on nicely, you can clearly see 5-member lactone with 1 methyl group. The concept you have to learn here is if starting material has strainful ring, strain will be relieved because of ring expansion during Baeyer Villiger oxidation. Then the next example. Here you have cyclohexanone. Second position you have dimethyl group. You are using the peracid. You should find what will be the final product. The starting material has carbonyl. You are using the peracid. So Baeyer Villiger oxidation. First step will be usual one. Nucleophilic addition on carbonyl. It creates new CO bond. The addition on the carbonyl leads to the unstable carbon because carbon attach with many heteroatoms. So one carbon should migrate. Which carbon migrates? Here you have quaternary carbon as well as methylene carbon. Methylene carbon migrates because of steric effect. If you look at the cation stability or migrating ability, you might commit the mistake because priority of steric effect is higher than the migrating ability. So methylene carbon migrates, you have new CO bond. The migration leads to the ring expansion, the insertion of oxygen. So you have the cation near the alcohol. It quenched as carbonyl. If you read on nicely, you can clearly see 7-member ring with heteroatoms. You start from 6-member, end up with 7-member. The concept you have to learn here is priority for steric effect is higher, which invert the migrating ability. Then the next example. Here you have cyclohexanone. Second position you have vinyl group. You are using the peracid. You should find what will be the final product. The starting material has carbonyl. You are using the peracid. So Baeyer Villiger oxidation reaction. First step will be nucleophilic addition on carbonyl. Peracid adds to the carbonyl, which creates new CO bond, which makes the carbon unstable. You have to migrate the carbon. Which group migrate? The cation stabilizing species migrate. According to that, here we have secondary and tertiary carbon. Tertiary carbon can stabilize the cation better. So tertiary migrates. It attaches with vinyl group. So it has extra one carbon. So it migrates. So the vinyl group migrate. You have the cation near the alcohol. Cation considers ketone by the hydrogen elimination. If you read draw nicely, you can clearly see 6-member ring will become 7-member ring. The concept you outline here is in Baeyer Villiger oxidation, cation stabilizing group migrates. Here, tertiary can stabilize better than secondary, so it migrates. Then the next example. Here you have carbonate, one side with phenyl, another side with nitrobenzene. You are using the peracid. You should find what will be the final product. The problem is all about migrating ability. We will see why. The starting material has carbonyl. You are using the peracid. So first step will be nucleophilic addition on carbonyl, which creates the new CO bond and O minus, which makes the carbon unstable. So migration has to be happened. Here, which group migrates is the real question. The NO2 is the electron withdrawing group. It makes the ring electron less denser. So electron density of A ring is less than B. So B ring should migrate, create the new CO bond. The migration leads to the carbonyl formation as well as CH3COO minus elimination. Here shown as the concerted mechanism. All three steps happen simultaneously. Migration of carbon, which is first one, then CH3COO minus is the second one, then carbonyl formation. If you read it nicely, you can clearly see oxygen inserted between phenyl ring. The concept you have to learn here is in phenyl system, electron richer ring migrates. Then the next example. Here you have dicarbonyl system with two methyl group. You are using the peracid. You should find what will be the final product. Here the reaction is kind of special reaction because you have two carbonyl nearby. The migrating ability of the carbonyl is higher because the final product is much more stable. Anhydride is the favorable product. What happens is carbonyl group migrates. Here you have carbonyl and you have peracid. What really happens is nucleophilic addition on the carbonyl. The addition leads to the carbon instability because many heteroatoms on carbon. So carbonyl migrates, you have new CO bond. During the migration, RCOO minus elimination, you have new CO bond. The migration leads to the cation near the alcohol. Migration happened, you have carbonyl. If you read on nicely, you can clearly see anhydride. The concept you have to learn here is dicarbonyl system, the product end up with always anhydride. Then the next example, here you have cyclopentane system. Two methyl groups are trans to each other and you have carbonyl with methyl group. You are using the peracid. You should find what will be the final product. Here starting middle kind of given us tricky one because it is given like carbohydrate. We stick with basics, do the reaction. Here you have carbonyl and acid. So Baeyer Villiger oxidation. First step will be nucleophilic addition on carbonyl. New CO bond form, new HO bond forms. The addition makes the carbon unstable. So carbon migrates. Which carbon migrate? Primary or tertiary? We already know tertiary can stabilize the cation better. It migrates. So ring carbon migrate. You have new CO bond. The migration leads to the cation near the alcohol which form carbonyl there. If you read it nicely, the product is ester with side chain ring. The concept you have to learn here is always stick with basics, do the mechanism, find the product. Don't get confused with stereochemistry or structure or configuration. Then the next example. Here you have cyclohexanone, one side methyl group, another side isopropyl group, methyl above the plane, isopropyl below the plane. You are using the peracid. You should find what will be the final product. The starting material is interesting because stereochemistry specified. We have to maintain the stereochemistry during the reaction. The starting material has carbonyl. You are using the peracid. So nucleophilic addition on the carbonyl. New CO bond, new HO bond forms. Here the carbon is unstable because of many heteroatoms. You have to migrate the group. Which group migrate? Here you have secondary and tertiary nearby. Tertiary is interesting because it is with stereochemistry. As we already know, Baeyer Villiger oxidation always end up with retention of configuration. So tertiary migrates with same configuration. So carbon migrate. You end up with cation near the alcohol. The cation considers carbonyl by the hydrogen elimination. If you look at it clearly, ring is expanded from 6-member to 7-member ring with the retention of configuration. The same methyl above the plane, same isopropyl below the plane. The relationship also maintained the same. The concept you have to learn here is in Baeyer Villiger oxidation, retention of configuration happened. Then the next example. Here you have cyclopentanone. Second position you have methyl group. You are using the peracid. You should find what will be the final product. Here you have carbonyl. You are using the peracid. Then you have the chances of Baeyer Villiger oxidation. First step will be the nucleophilic addition on carbonyl. You have new CO bond, new OH bond. The addition leads to the carbon unstable because it is attached with many heteroatoms. So carbon has to migrate. Which carbon migrate? according to the migrating stability. Electron stabilizing carbon migrate. Here you have secondary and tertiary. So tertiary has highest priority. It migrated towards oxygen. It migrate. You have cation near the alcohol. Cation considers carbonyl by the hydrogen elimination. If you redraw nicely, you end up with 6 member. If you notice that 5-member ring will become 6-member ring. During the process, ring strain is relieved. It goes from unstable system to stable system. So ring can assist the whole reaction. So the concept you have to learn here is, in the strainful system, ring strain will be relieved because Baeyer Villiger oxidation promote the ring expansion. Then the next example, here you have cyclopentanone. Second and third position you have 3-member fused ring. You are using the peracid. You should find what will be the final product. Here starting material may be tricky, but our reaction center is away from difficult structures. So it has the carbonyl. We focus on the carbonyl and peracid. So Baeyer Villiger oxidation. First step will be nucleophilic addition on the carbonyl. New CO bond, new OH bond. The addition leads to the carbon unstable because carbon attached with many heteroatom. So one carbon should migrate. Which will migrate? You have secondary and tertiary carbon. Tertiary will migrate because it can stabilize the cation better. So carbon migrates. You have cation near the alcohol. The cation near the alcohol form the carbonyl. End up with final lactone. Lactone is ester in the ring system. You end up with final product. Here the cyclopropyl structure don't contribute anything, just given as a distraction. If you look at the another fact that you have 5-member strainful ring which convert into 6-member ring. During the process, strain will be relieved because 5-member ring is strainful because of bond angle. It becomes 6-member by oxygen insertion. The insertion makes the ring less stable to more stable. The concept you have to learn here is, always focus on functional group, conduct the Baeyer Villiger oxidation. Then the next example, here you have cycloheptanone, 7-member ring. Second position you have ethyl group which is stereochemically specified below the plane. You are using the peracid. You should find what will be the final product. The starting metal may have cyclic ring, but our concept is simple. We have to find the carbonyl, do the nucleophilic addition. Here you have carbonyl and peracid. So Baeyer Villiger oxidation, it's a rearrangement reaction. First step will be attack on carbonyl, nucleophilic addition of peracid to the carbonyl, which form new CO bond and OH, which makes the carbon unstable. So one carbon should migrate. Here two asymmetrical carbon is there, secondary or tertiary. Tertiary can stabilize cation better. So tertiary migrates. You have cation near the alcohol. Then cation has to be quenched. It quenched as carbonyl. You end up with ester. During the rearrangement, oxygen is inserted. So ring expansion happened. Here no change in the stereochemistry occur because chiral carbon with retention of configuration. The concept you have to learn here is, in Baeyer Villiger oxidation, retention of configuration happened. Then the next example, here cyclohexane is given, which is in the chair form. You have isopropyl, methyl and acyl group as the substitution. You are using the peracid. You should find what will be the final product. Here cyclohexane in chair form is given, but our focus completely on carbonyl. We have carbonyl and peracid mean Baeyer Villiger oxidation. Here cyclohexane chair form don't play any role here. It's just a substitution. It given for distraction. So first step will be nucleophilic addition on carbonyl. As it attacks the carbonyl, you have new CO bond and OH bond. Carbon with many heteroatom is unstable, so one carbon has to migrate. Here two possibility, methyl can migrate and ring can migrate. The ring is electron richer, so it can migrate. So it migrates to oxygen and form the cation near the alcohol. The cation has to be quenched. It quenched as carbonyl by the hydrogen elimination. If you redraw nicely, you end up with ester. Here, tertiary group has higher migrating ability than primary because it can stabilize the cation better, so it migrates. The concept you have to learn here is you should not get confused by big structures or different configuration. You just focus on functional group and rearrangement and oxidation. Then the next example, here you have cyclohexenone, third position you have bromine, second position you have alkene, that is alpha, beta unsaturated ketone. You are in the peracid. You should find what will be the final product. The starting material is alpha, beta unsaturated ketone. Attacking species is nucleophile. So question is given for confusion whether the addition is 1,4 or 1,2 addition. Here 1,2 addition is favorable. If you are interested, go and study Michael addition separately. Here our focus is Baeyer Villiger oxidation. First step will be nucleophilic addition on carbonyl. So peracid attacks the carbonyl. You have new CO bond. You have new CO bond and OH bond, which makes the carbon atom unstable. So one group has to migrate. Which will migrate? As we discussed, electron rich group migrate. Here alkene side will migrate. You have new CO bond. Migration leads to the cation. So cation has to be quenched. It quenched as carbonyl. So if you redraw nicely, you have new 7-member ring with bromine, alkene and ester. The concept you have to learn here is peracid always undergo 1,2 addition, form the Baeyer Villiger oxidation product. Then the next example, here you have fused system, 5-member and 4-member ring. 4-member ring is the ketone, 5-member contain alkene and connecting hydrogen atoms into each other above the plane. You are in the peroxide and acetic acid. You should find what will be the final product. Here starting material is the fused system, but our focus is on carbonyl. But alkene is there. You may wonder whether epoxide can form or not. Nucleophile is OO minus. It cannot attack the alkene because it's a electron rich ring. Electron repel each other. So attack don't happen in the alkene there. So only possibility is carbonyl, which has positive charge on carbon. Attack happen. So nucleophilic addition happen on the carbonyl. New CO bond forms. The migration leads to the cation formation. The migrating group is the tertiary carbon. Here you may confuse which group migrate. Tertiary group migrate because it can stabilize the electron better, but it is also a chiral carbon. So chiral carbon migrate without losing its configuration, form new CO bond. The migration leads to the cation near the alcohol. If you redraw nicely, it will form ketone by hydrogen elimination. So you start from 4-member ring, end up with 5-member ring. This problem contains many important facts. First one is chemoselective. Peroxide don't react with alkene. Second one is chiral carbon migrates with same configuration. Third one is strain can assist the Baeyer Villiger oxidation. Then the next example. Here you have cyclohexane attached with carbonyl and methyl. Technically it's a ketone with methyl and cyclohexane. You are using the peracid. You should find what will be the final product. The reaction is simple. Starting material is ketone. Reagent is peracid. So Baeyer Villiger oxidation. First step will be attack of acid and carbonyl. It's a nucleophilic addition reaction. So new CO bond forms which makes the carbon unstable. So one group migrates for stability. Here you have two choices. Primary can migrate or ring carbon which is tertiary can migrate. If you look at the stability, tertiary has higher stability, so it migrates. Tertiary can stabilize the cation better, so tertiary has highest priority, so it migrates to the oxygen. The migration leads to the cation near the alcohol. Then cation quenched as carbonyl end up with final product. The concept you have to learn here is tertiary has higher migrating ability than primary. Then the next example, here you have to find the starting material. Reagent is mCPBA, meta-chloroperbenzoic acid. Product is the bicyclic compound with the ester, alkene and O-benzyl. You should find which kind of starting material can produce the product. If you look at the product is ester, so it can be a product of Baeyer Villiger oxidation. So let us start with carbonyl with one oxygen less. So ring size also less. So first step will be attack of metachlorobenzoic acid. Here I simply given as RCOO minus. It attacks the carbonyl. You have new CO bond. Since carbon attached with many heteroatom, it has to be stabilized. So what really happened? Carbon should migrate. Which carbon migrate? Here we have secondary and tertiary. Tertiary has higher migrating ability, so it migrates. You have RCOO minus, so new CO bond forms, and cation also form near the alcohol. Cation has to be quenched, so it quenched as carbonyl. If you redraw nicely, we get the required product. So the concept you have to learn here is always master the retrosynthesis. It's a kind of reverse engineering from product to reactant. Then the next example, here you have carbonyl. The starting material is ketone, one side methyl, another side cyclopropyl. You are using the peracid. You should find what will be the final product. Here the problem is all about migrating ability because you have cyclopropyl here. Let us go by the basic. Here you have carbonyl and peracid. First step will be attack of carbonyl with peracid. It is a nucleophilic addition reaction. New CO bond form which makes the carbon unstable. So which group migrate is a real question. Here you have methyl and cyclopropyl. Cyclopropyl migrates because it has higher stability. We will see the reason shortly. The migration leads to the ester. If you redraw nicely, you end up with final product where oxygen inserted between cyclopropyl and carbonyl. Let us see why cyclopropyl is more stable. We already seen in the basic. Let us see again. Because you have cation, which cation can be stabilized over cyclopropyl because of its perpendicular p orbital. The p orbital provide the resonance-like stability. So cation migrates to the carbon. Further, it has the aromaticity because migration with 4n plus 2 electron give the aromatic cation. Aromatic cation is stable. That's why it migrates. The concept you have to learn here is cyclopropyl systems are more stable than any other group. Then the next example, here you have bicyclic system with one bridged carbon, alkene and carbonyl. You are using the peracid. You given three possibility. One is oxidation at the alkene. Second is oxidation both in alkene and carbonyl. Third is only oxidation at the carbonyl. So you should find among the three which is the major product. The reaction is all about basics. The question is given on fundamental whether the peracid can attack alkene or ketone. Alkene is pi electron. Peracid is the nucleophile. Nucleophile has negative charge. alkene has rich of electron. So both are in same charges, repel. So oxidation never happen on the alkene. So we simply eliminate all other product. Only possibility is oxidation happen on the carbonyl, which is Baeyer Villiger oxidation. So let us conduct the Baeyer Villiger oxidation. First step will be addition of nucleophile to the carbonyl. So new CO bond form. You have O minus and new CO bond. The addition makes the carbon unstable. So one carbon migrates for its stability. Here you have two choices, tertiary and secondary carbon. Tertiary carbon can stabilize the electron better. It has higher migrating ability. It migrates. You end up with carbonyl and ring expansion. That is our major product. The concept you have to learn here is peroxide never reacts with alkene and never form epoxide. Then the next question. Here you have carbonyl which is in the bicyclic system. Two bridged methyl group, one connected methyl group. You are in the peracid. You should find what will be the final product. The similar kind of problem we already seen because near to the carbonyl bulky system is there. We will go by step. You have carbonyl and you have peracid. So it is a Baeyer Villiger oxidation. So first step will be addition of peracid to the carbonyl. It is the nucleophilic addition reaction. The addition leads to the carbon unstable because carbon attached with many heteroatom. So one carbon should migrate. Which carbon migrates? Bulky carbon cannot migrate because of its bulky steric effect. Steric crowding don't allow the attack as well as don't promote the migration. So only possibility is secondary carbon migration. It migrates. You have insertion of oxygen, carbonyl formation. The ring expansion happen along with the transformation. You end up with final product. The concept you outline here is steric effect can change the migrating ability of the compound. Then the next example, here you have cyclohexanone. Second position you have trifluoromethyl. You are using the peracid. You should find what will be the final product. Here the question is about migrating ability, whether CF3 migrates or not. Here starting material you have carbonyl, reactant is peracid. So nucleophilic addition on carbonyl which leads to the new CO bond. The CO bond formation create the instability of carbon because of many heteroatom. So one group has to migrate. Which group migrate? Whether trifluorocarbon or a methylene group. Here trifluorocarbon is the electron withdrawing group, so it cannot migrate because it will destabilize the cation. So methylene group migrates. So methylene group migrate. It form new CO bond and ring expansion. So you end up with lactone with 7-member ring. The concept you outline here is during the Baeyer Villiger oxidation, the carbon with electron withdrawing group has the lower migrating ability. Then the next example, here you have ketone, one side tertiary butyl, another side phenyl. You are using the peracid. You should find what will be the final product. Here you have carbonyl. You are using the peracid. So nucleophilic addition on carbonyl happen. You have new CO bond and O minus. The addition leads to the unstable carbon. So one group should migrate to create the stability. Which group migrate? Here the competition between phenyl and tertiary butyl. Tertiary butyl has the highest migrating ability. So it migrates, new CO bond form and carbonyl form through the concerted mechanism. If you redraw nicely, you can see oxygen inserted between carbonyl and tertiary butyl. The concept you have to learn here is tertiary butyl group has higher migrating ability than phenyl group. Then the next example, Here you have bicyclic system, two methyl group, one bridged methyl group and one ketone. You are using the peracid. You should find what will be the final product. Here structure may be confusing, but our focus is on functional group, that is carbonyl. So you have carbonyl and peracid. So Baeyer Villiger oxidation. First step will be the nucleophilic addition on carbonyl, new CO bond. The addition leads to the O- and CO bond formation, which makes the carbon unstable because it is attached with many heteroatoms. So one group migrate. Which group migrate? Here tertiary butyl group can migrate because it is the ring carbon with more electron donating ability. So it migrates, not the methyl group. So migration leads new CO bond and carbonyl formation. You end up with ester. If you redraw nicely, you can clearly see oxygen inserted between carbonyl and the ring. The concept you have to learn here is ring carbon can also migrate if there is less steric effect. Then the next example, here you have adamantane system. It's a benzene with attachment of one cyclohexyl fusion ring system. It's a kind of multiple cyclohexyl system in chair form. You have one ketone there and you are using the peracid. You should find what will be the final product. Here carbonyl is there, peracid is there. So nucleophilic addition on carbonyl. Don't get confused with bigger structure. Here our concept is simple. We focus on functional group and reagent, find the product. So first step will be nucleophilic addition on carbonyl. New CO bond forms. The formed new CO bond create the unstable carbon because it's connected with many heteroatoms. Here the carbon is symmetrical. Both side carbon atoms are same. Anything can migrate, form the same product. So carbon migrate. CH3COO minus eliminates and the carbonyl formation. All three happen at the same time. You have the ring expansion. If you redraw nicely, you can clearly see 6-member ring becomes 7-member ring. The concept you have to learn here is always focus on the basic. Don't get confused by the big molecules. Then the next example, here you have bicyclic system with carbonyl, 2-methyl group and tertiary butyl group with the side chain. You are using the peracid. You should find what will be the final product. As we discussed already, we focus on the basics. First you have carbonyl and peracid. So chances of Baeyer Villiger oxidation. So peracid attacks the carbonyl through the nucleophilic addition, which creates new CO bond and OH bond. The new bonds makes the carbon unstable. So one carbon should migrate. Here tertiary has high steric effect. Even though it can stabilize the carbon, tertiary butyl group cannot migrate. So methylene group migrate. You have new CO bond and cation near the alcohol. Cation near the alcohol quenched as carbonyl. You end up with ester and ring expansion. The concept you have to learn here is steric effect has highest priority over migrating ability. If the migrating group is steric, it cannot migrate. Only the lowest priority group migrates. Let us summarize what we learned. What is Baeyer Villiger oxidation? It's a conversion of ketone into ester by using peracid. The catalyst can be any peracid, maybe the combination of peroxide with the acid. More simply, the compound donate the oxygen. Then which group migrate mean cation stabilizing group migrate. Highest priority will be hydrogen, lowest priority will be methyl. Then one important fact is cyclopropyl cation is super stable. It will migrate first. Then the very important thing, if the compound is steric, always less steric side migrate. The migrating ability will be reversed. The final fact is in cyclic system, Baeyer Villiger oxidation expand the ring.